Welcome back again, viewers, as we continue with our review of the physics topic for O and A levels physics. Today, we are going to be looking at moment of a force about a point. When we are done with this, we are going to try to cross into equilibrium, because we are going to need a larger part of what we are going to learn under moment of a force in equilibrium. So, let us start. Moment is one of the quantities that we have to learn in physics. Most of the time, we just get to see it as moment, but the full name should be moment of a force about a point. That is the complete name. When you call it moment, it's like an abridged form of the name. It is fully referred to as a moment of a force about a point. Oftentimes in physics, we can have questions like mentioning we can be required to mention the effect of a force on an object. There are so many things that a force can do on an object. A force, of course, can make an object to move. It can make an object to rotate. It can make an object to turn. It can stop an object that is already moving. And a force can crumble an object. A force can straighten an object. There are so many things that a force can do on an object. But the turning effect that a force gives to an object, the turning effect that a force gives to an object is what is called the moment of a force about a point. The moment of a force about, if an object is going to move, for example, if I have my marker and I want that object to turn, I want this marker to turn, the very first thing I must do is to hinge it or hold it at a point. If I hold it at a point and I exert a force on it at any other point, and I exert a force on it at any other point, either an upward force or a downward force, it will turn. Once it is hinged or held at a point and you exert a force on it at some other point, it must rotate, it must turn. The turning effect that the force gives to an object is what we call the moment of a force about a point. So it is necessary for us to understand that before an object can turn, there must be two things. The object itself must be held at a point, and there must be an application of a force at some other point. If you are going to open your door, you know your door opens by turning. It has already been hinged to the wall at some point. All you just need to do is to exert a force on the door at some other point, not the point where it was hinged, but at some other point. Then the door will open by turning. Anything that is going to turn, anything that is going to rotate must first be hinged at a point, and there must be an application of a force on it at some other point. So the moment is the turning effect that the force gives to an object. And it is a quantity that we can determine. It is a quantity that we can determine. And the determination of moment of a force about a point is what you will get in the definition of moment of a force about a point. So if I'm asked to define the moment of a force about a point, I will say that the moment of a force about a point is the product of the force and the perpendicular distance between the line of action of the force and the point about which the moment is required. The moment of a force about a point, the moment of a force about a point is the product of the force and the perpendicular distance between the line of action of the force and the point about which the moment is required. That means anytime I wish to find moment, there must be two quantities that I will have to multiply, products. I must multiply the force, because I told you earlier that before we can have moment, there must be the application of a force. So I must multiply the force by not just any distance, by the perpendicular distance between two things. What are those two things? The line of action of the force and the point about which you want to find the moment. When we say the line of action of a force, what do we mean? Thank God we are coming from a point where we have already treated scalars and vector. Force is a vector quantity, and vector quantities, I told you, are represented with a line that has an arrow. The arrow shows the direction in which the force is acting. Now, if you use a line and this arrow to represent a force, this line, whether extended in the forward direction or extended in the backward direction is what we refer to as the line of action of a force. And the line of action of a force can be extended to any point. If I have a point here, the distance, let us assume that this is the force, and let us assume that this is the point about which I want to find the moment of this force. There are so many distances between this point and this force. This is a distance, this is another distance, this is another distance, this is another distance, and this is another distance. There are so many other distances, infinite number of ways by which I can draw a line representing distance from this point to this force. But there's only one distance that I need. It is the distance that makes 90 degrees between the point and the line of action of the force. So if I want to find the moment must be the product of this force and the perpendicular distance that you have drawn from the point to the line of action of the force. It is necessary that we do this because there are so many other quantities. There are some quantities in physics that are also obtained by force times distance. A very good example is work. Work in physics is also force times distance. So it is necessary that anytime we are using this force times distance formula, we must specify the distance so that we will not be finding one when the question has asked us to find the other. The distance that we use in work is the distance that is along the force. It is the distance that is along the force. The distance that you are going to use to calculate work is the distance that is in the same direction with the force. That is why they say that work is done only when force is exerted on an object and the object moves in the direction of that force. So the distance that you need to calculate work is the distance that is along the direction of the force. But that is not the same here. The distance that we use to calculate moment is the distance that is making 90 degrees with the force. So I will go over the definition of moment again. Moment is the product of a force and the perpendicular distance between the line of action of the force and the point about which the moment is required. It is a vector quantity. The unit of moment is generally the unit of the force, which is usually Newton, and the unit of distance, which is meters. If you multiply the two of them together, you will have Newton meters. So the unit of moment is Newton meters, and it has a direction. So that is what makes it a vector quantity. The force you are using to calculate it is a vector quantity. Moment itself is a vector quantity. We are going to see later what are the directions that moment can take. But for now, let us take it like it is a vector quantity and its unit is Newton meters. Mind you, Newton meters can also be used as the unit for work, though work is usually put in joules. But joules and Newton meters are dimensionally the same unit. Joules, where you should use joules, if you use Newton meters, you are correct. And anywhere you are expected to use Newton meters, if you use joules, you are still correct. So it is expected that you know that the two of them are equal. Now, what we want to do is to see the different ways by which questions on moment can be set and how we are going to calculate each for each of those means by which you can get the moment. We can be given a rod or a plate or a plank or a ruler, and we will say that a force is exerted on it. Let's assume that the plank is horizontal and a vertical force is exerted on it. Let us say that the force is 7 Newton. There's a point A. There's another point along the end, which is B. The distance from B to A, let us call it 7 meters. 7 meters. The distance from A to where the force is. Let me call the point where the force is. Let me call it point C. I'll say that the distance from A to C is 5 meters. I can be asked to find the moment. I told you anytime you want to find the moment, they must specify the force and they must specify the point. I cannot just, for example, in this question, ask you to find the moment of 7. That is wrong. That is incomplete. I must tell you the point and I must tell you the force that I expect you to find the moment through. I can ask you, for example, in this question, to find the moment of 7 about point C. I can ask you to find the moment of 7 about point A. I can ask you to find the moment of 7 about point B. In each of those questions, I've given you the force 7 and I've given you the point. Let us assume that I want you to find the moment of 7. The moment of 7 about point A. All I need, remember, moment is the product of the force and the perpendicular distance between the force or the line of action of the force and the point. The force in this case is clearly 7 Newton, while the distance is, this is 7. I want to find the moment of 7 about point A. The distance from A to 7 is clearly 5. And we can see that the axis is actually perpendicular to that 7. The axis is actually perpendicular to that 7, so I'll just multiply it by 5 meters, and that should be 35 Newton meters. We are still going to come back to describe the direction, but for now, let us get busy with how to determine the moment in the first case. I can also be asked to find the moment of 7 about point B. The moment of 7 about point B must be equal to the force, that is 7 Newton, multiplied by the perpendicular distance between the line of action of the 7 and the point B. The perpendicular distance between B and the line of action is 12 meters. How did I get that 12? From B to A has been given to be 7. From A to C has also been given to be 5. If we add them together, we'll get 12 meters. So if I multiply 7 Newton by 12 meters, I should have something that looks like 84 Newton meters. And that is the moment of 7 about point A. This is the moment of 7 about point B. So we'll move on with more examples. I can be asked to find the moment of, okay, that same 7 now acting along the horizontal direction. This is point A and this is point B. The distance between B and A, let us assume, is 10 meters, while the force itself, now horizontal, is still 7 Newton. Now, the question is that we should find the moment of 7 about point A, and we should find the moment of 7 about point B. Clearly, the moment of 7 about point A will be force multiplied by the distance. What is the force in this case? 7. But like I said, we are not just using any distance. Yes, the distance is given, 10 meters. But you have to be very sure that it is the distance that you need to solve the question. So 7 meters is the force. I want to find the perpendicular distance between 7 and A. If you check, 7 is exactly placed on A. It is passing through A. It has no perpendicular distance to A. If 7 had been placed like this, and point A has been placed like this, then we can say that there's a distance between 7 and A that is perpendicular. But 7 is exactly passing through point A. It does not have any perpendicular distance away from it. It is along A. If you are along the axis of an object, you are at no perpendicular distance from that object. So the distance is actually going to be 0, and that becomes what? 0. The moment of 7 at point B is force 7 multiplied by the distance. What's the distance of that 7 from B? The distance of 7 from B will still be the same thing, because the 7 is placed along the axis that is passing through B. If you extend the line of action of 7, you will see that it will still pass through B. So the distance will still be 0 and the moment will be 0. 7 times 0 is 0. So therefore, I will say by extension that any time the line of action of a force passes through a point, the force will not have moment at that point. Any force whose line of action passes through a point will not have moment, or its moment at that point will be equal to 0. A force will not have moment at any point where its line of action is passing through. So I've been able to say it in using different expression, so that you at least get one of it, which still means the same thing. So there are more examples that we can take. I can give you a vertical plank this time, and our 7 is placed horizontally. This is point A, this is point B, and this is point C. Let us assume that the distance between B and C is 12 meters. The distance between B and A is 15 meters. And we are asked to find the moment of 7 about point A, the moment of 7 about point B, and the moment of 7 about point C. Moment of 7 about point C. If we need to do that, what's the moment of 7 about point A? This is 7. Moment, don't forget, is the product of the force and the perpendicular distance between the line of action of the force and the point. So we can say that the force here is 7. What is the perpendicular distance from A to 7? This is the distance. The distance from A to 7 is this distance. It is 15 meters because A to B is 15 meters and 7 is placed exactly on B. So the moment will be 7 times 15, and 7 times 15 is 105 Newton meters. What is the moment of 7 at point B? The force 7 times perpendicular distance. Since 7 is placed on B, its line of action will pass through B. A force will not have moment at any point where its line of action is passing through. So that will be 7 times 0 because it's not going to have any perpendicular direction and perpendicular distance away from that point. 7 times 0 is 0. So the moment of 7 at point B will be 0. Let us go to moment of 7 at point C. This is point C, and this is where 7 is. Between the two of them, there's a perpendicular distance, and that distance has been marked 12. Perpendicular distance has been marked 12. So the moment of 7 at point C will be 7 multiplied by what is the perpendicular distance? 12. If you multiply 7 by 12, we'll have 84 Newton meters, and that is the moment of 7 about point C. We move on with more intriguing examples. Let us assume that we have another point A, and we have a force 7 Newton, still 7 Newton, and it is acting at 30 degrees to the axis of the plane that leads to A. Let us assume that this point is point B, and the distance between point A to point B is taken to be 15 meters. In this question, we have to find the moment of 7 about point A. The moment of 7 about point A. How do we do this type of question? The very first thing is, one way by which you can attempt this, which will be very, very wrong, is for you to just multiply 7 by 15 to get the moment of 7. This is the first 7. I thought the distance is 15 from A. We are not going to use that 15. Why? We are not going to use that 15 simply because that 15 is not perpendicular to 7. Any distance that you are going to use to multiply the force anytime you want to determine the moment must be a perpendicular distance. We can clearly see that the distance that is given to us in this case is placed at 30 degrees to the vector. So we cannot use it. The distance that we are expected to use must be perpendicular. Perpendicular means the distance must form 90 degrees with the force, as we have here. The distance we use here and the force are at 90 degrees to each other. The distance that we use here and the force are at 90 degrees to each other. So what we are going to do here is what I taught you under, what you have been able to discuss under resolution of vector. We are going to try to see if we can resolve this 7 Newton. I told you, anytime you have an inclined vector, it is possible for you to resolve it into horizontal and vertical components. You can easily resolve it into horizontal and vertical components. When you understand, because horizontal and vertical components are two components that we are so used to from our mathematics, from our early days with mathematics, we understand what vertical axis means and what horizontal axis means. So we can easily resolve a vector into both horizontal and vertical. And how do we get this done? What we will do is we'll go to the point of origin of that vector, the point where that vector is meeting the plane. We'll draw our vertical component beside it. Vertical is an axis that is along Y. We'll draw our horizontal component beside it. Horizontal component is the axis along X. We'll draw the two beside it. Then we can now resolve the vector. How do we resolve this vector? We'll simply just resolve. And remember, there's a short way to resolve. I said the component that you have beside the vector itself is the cos. The other component is the sine. So if I want to resolve this 7, the horizontal component is clearly beside the angle. The angle given is the angle between 7 and the horizontal component. So I can just resolve that angle as 7 cos 30 while I can resolve this as 7 sine 30. If you are still having problem with this, I want to advise you to check our material on scalars and vector. We have sufficiently discussed how to resolve a vector into horizontal and vertical components. So once that is done, I don't need the original vector anymore. Once you have resolved a vector, you don't need the original component anymore. You don't need it. So you can clean it off and try to see how you can now approach the question with what you have left. And this is very simple. We have been able to break the vector into two different forces. We have been able to break that 7 Newton into two vectors. One is 7 cos 30, the other one is 7 sin 30. So we can now resolve them into, we can now use them to determine the moment, because that is what the question wants us to find. The question wants us to find the moment of 7 at about point A. So we'll try to see if we can find the moment of the two vectors that we now have. 7 cos 30, I hope you can see, will not have moment at A. Why? It is passing through point A. It will not have moment at A because it is passing through point A. A force will not have moment at a point where its line of action is passing through. If you extend the line that you have used to represent a force and it is passing through a point, it will not have, that force will not have moment at that point. Some other forces can have moment at that point, but if one whose line of action is passing through a point will not have moment at that point. So 7 cos 30 is not going to have any moment. You can even try to do it. It will be 7 cos 30 multiplied by 0. There is no perpendicular distance between this 7 cos 30 and A. But let us check for 7 sin 30. The force this time is 7 sin 30. We are going to use it to multiply the distance. We can see that this is 7 sin 30. This is the line of action of 7 sin 30. This is the point. There's a perpendicular distance that we can bring from here to here. And luckily, that has also been given to be 15 meters. 15 meters is the distance from this A to the B where you have placed the force. So I will use that distance as my distance. So now I can easily find what I need. The moment, mind you, this is in Newton and this is in meters. The moment will be 7 sin 30 is 3.5 Newton multiplied by 15 meters. If we multiply that, that should be 52.5 Newton meters. And that is our final answer to this question. 52.5 Newton meters is the moment of that 7, already now splitted into 2, about point A. That's easy. We'll take more questions, just one more to now the question is that we should find the moment of 20 about point C, and we should also find the moment of 10 about point A. That is a question that we wish to answer now, so that we'll see other forms by which the question on moments can be set. Other forms or even more intriguing forms by which the question on moments can be set. So now, how do we find the moment of 20 about point C? This is the 20 Newton force. This is the point C. Let us assume that the directions are given. Let's assume that this is 5 meters and the distances are given. And this is 7 meters also. So now, the very first thing is we can see that the distances looks vertical, but our forces are inclined. 20 Newton is inclined, 10 Newton is also inclined. So we can, when you have inclined vectors, for majority of the time, it is necessary for you to resolve them. That's why it is necessary for you to understand the resolution, the process of resolution of vector, because you are going to be needing it, because the aspect of resolution of vector is one aspect that is always creeping into almost every other aspect in physics. So I'm going to resolve this 20 Newton. And luckily or unluckily, we have angle 120 degrees. We have 20 making an obtuse angle. How do we resolve with an obtuse angle? It is not necessary you use that obtuse angle. I'm expecting you to know as a science student that this is a straight line. If this is a straight line, this angle is 120 degrees. It means the other angle will be what? 60 degrees. Because angle on a straight line is 180. And if angle on a straight line is 180, and a part of it is already 120, the remaining part can just be 60. So I can as well resolve with 60 as much as I can resolve with 120. But it is always good where you can find the acute angle to resolve with the acute angle. It's always good, easier, and better to resolve with the acute angle. Now I want to resolve 20. How do I resolve with 20? Draw from the point of origin, draw the two components. And the two components that we have been using are the horizontal and the vertical component. I will draw the horizontal component just beside that 20, and I'll draw the vertical component also just beside that 20. So I'm going to find them. Now, I told you how to resolve very quickly. The component beside the angle is the cos. The other component must be the sine. How do I resolve this? This should be 20 cos 60, while this should be 20 sine 60. Always remember that. And once you have resolved a vector, you don't really need that vector anymore. You have been able to break it down into the components that will be easy for you to understand. So I can remove those components. I can do the same thing to 10 Newton at 45 degrees. I will do the vertical component beside it from the same point where it's starting, the vertical component, and the horizontal component beside it from that same point. The horizontal component, the component beside the angle is 45, is the vertical component. And I'm going to write that as 10 cos 45. The other component here will be 10 sine 45. If you know one component, you should know the other. 10 sine 45. If that is the case, I can now remove my 10. The reason why I'm removing it is so that the diagram will not look too rough for you to understand. So that's why I'm removing all of this other part of the question that I will not be needing anymore. So I can now find the moment that they want me to find. Number one, 10 cos 45 and 20 cos 60 will not have moment at any point. Both of them, if you extend them, they are meant to be on that line. The two of them are along this line. They are along, if we extend them, they will pass through C. If we extend them, they will also pass through A. So the two of them will not have moment at either point C or at point A because they are along point C and point A. And I told you that forces will not have moment at any point where their line of action is passing through. So I'm going to remove those ones too. Now, if you want me to find the moment of 20 about point C, the only part of 20 that we have moment at point C is 20 sine 60. If you want me to find the moment of 10 at point A, the only part of 10 that we have moment at point A is 10 sine 45. So now, if I want to find the moment of 20 at point C, I'm still going to use the same formula, the force multiplied by the perpendicular distance. And what is the force in this case? The force is 20 sine 60 multiplied by what is the distance? The distance is going to be the perpendicular distance between that force and A. The distance, the perpendicular distance between that force and A, and that distance is 5. If I multiply that, I should have moment of 20 about point C. 20 multiplied by sine 60 is 0.866 multiplied by 5. If we multiply everything, we are going to have 86.6 Newton meters. So if I'm looking for the moment of 10 about point A, I'm going to do the force, the only component of 10 that is left in the problem is 10 sine 45. Not that others are not even there. Other components are there, but they are not just relevant for the moment that we are trying to determine. 10 sine 45, I'm looking for the moment of that 10 about point A. Point A, the distance, perpendicular distance between this force and point A is given to be what? 5. So I can multiply by 5. I will have 10 multiplied by sine 45 is 0.7071 multiplied by 5. If you multiply that, we are going to have 35.355 Newton meters. And that is the formula, that's the value for the moment at that point. I hope with these few examples, we have been able to correctly, to sufficiently treat the determination of moment of a force about a point. There are now two types of moment. We said earlier that moment is the turning effect of an object. If an object is going to turn, it will either turn in one of two directions. It will either turn clockwise or anti-clockwise. If you have to turn, you are either turning like the hands of the clock, or you are turning against the hands of the clock. That is anti-clockwise. If an object, if this pen is going to move, if I exert a downward force at this end, it's moving in a clockwise direction. If I exert an upward force at this end, it will move in an anti-clockwise direction. So the two types of moments based on its direction are clockwise turning moment or anti-clockwise turning moment. So as from now, anytime we determine moment, we must be able to specify the moment that we have been able to calculate. Is it clockwise or anti-clockwise? I'll go back to the few of the examples that we have taken about moment to check which of them will be clockwise and which of them will be anti-clockwise. So let us start from 7 Newton. I'll just take one or two examples. 7 Newton at point A, when the distance between the two is 12 meters. 7 Newton at point A. I want to find the moment of 7 about point A. I want to find the moment of 7 about point A. The moment of 7 about point A must be equal to the force, 7 Newton, multiplied by the perpendicular distance between 7 and point A. Perpendicular distance between 7 and point A this time is, the force is 7. The perpendicular distance between the force and point A is 12 meters. The force itself is 7 Newton. That will be 84 Newton meters. But we are not done. We now need to verify if this moment is clockwise or anti-clockwise. If I want to determine that, I will pretend that I have this object in real life. This object that is 12 meters from 7 Newton. I will now assume that this end, this point, and this end A, where I am finding the moment about, is held. I will assume that I'm holding this end to the board. If I decide to hold this end of this long plank to the board, and I exert a downward force on it at the other end, and I exert a downward force, how will it turn? If I hold this at this end, and I decide to exert a downward force on it, I'm expecting it to turn in this direction. If it's going to turn in this direction, what direction is this? Is this clockwise or anti-clockwise? That is clearly clockwise. So that is how we determine it. You will assume that you are holding the object, the plank, the ruler, the beam, or whatever it is that you are giving. You will assume that you are holding it at the point where the moment is to be determined, about where the moment is to be determined, and you will assume that you are exerting a force in the same direction as the force for which you are finding the moment. What direction do you think that force will make the object to move about? If it is clockwise, you write clockwise. If it is anti-clockwise, you write anti-clockwise. So let's take one or two other examples, and we'll see comprehensively what clockwise and anti-clockwise turning moments can look like. The last example that we took about two objects in this direction, this is point A and this is point C. We're able to resolve this. This was 20. I think the angle that we have here was 60. Here we had 45, and here 10. Here we had 5 meters. And I think at this point we have 10 meters. So what we did the very first time was to resolve this vector into horizontal and vertical. We also resolved 10 into horizontal and vertical. Ultimately, the vertical forces of 10 and the vertical component of 10 and 20 were not as useful because we said they were along A and C. So we're able to resolve them, we're able to remove them from the equation. So we're only left with 20 sine 60 on this at this point, and we're only left also with 10 sine 45 at this other end. Then we remove the original vectors because they are not necessary again. So now we can find the moment. Now we can find the moment. We want to find the moment of 20. Let us assume we are looking for the moment of 20 at point C. We are looking for the moment of 20 at point C. You will assume that this plank AC, this rod AC, is held on the board at point C. It is held on the board at point C. And you exert a force in the direction of that 20 sine 60, which is to the east. If you hold the plank at point C and you exert a force in this direction to the east, how do you think the object is turning? It is going to turn clockwise. So the moment of this 20 sine 60 about point C is clockwise. What about the moment of 10 sine 45 about point A? The moment of 10 sine 45 about point A is going to be what? We'll assume that we are holding this plank at point A and we are exerting a force that is in the direction of 10 sine 45. The force that is in the direction of 10 sine 45 will be below A, and if it goes that way, we can see that it will move also in the clockwise direction. So that one will give us a clockwise moment. So that is how to determine the direction of moment. Moment can either be clockwise or anti-clockwise depending on the direction of the force and depending on where the point about which you are finding the moment is located relative to the point. Now, from what we have learned about moment, we are now going to proceed to equilibrium. So basically, anytime you exert a force on an object, the object should move. One of the effects of exerting a force on an object is motion. Force is responsible for motion. If I exert a force on an object, it means the object should move. Now, the movement that an object can observe now differs, because anytime there's a force on an object, we are still going to see it later when we get to Newton's law. If a force is exerted on an object, then that object must accelerate. Anytime there's a force, there must be an acceleration. Acceleration is always necessary before we can have a force. Acceleration is always necessary anytime we have a force. It's always going to be there whenever you have a force. Now, if an object if a force is exerted on an object, let's assume a 2 Newton force is exerted on an object, clearly that object will move. It is going to move because it's going to have an acceleration that will be impacted on it by the force that is exerted. Now, let us assume that this object is not, we have another 2 Newton force in the opposite direction now exerted on that same object. A force of 2 Newton now exerted on the object in the opposite direction. The question is, will the object move? What will happen here is one of two things. It's either the object will not move at all, or the object will move with constant velocity. Because here, the forces on the object have completely balanced. There's a motion that a 2 Newton force is trying to cause in a direction. There's a counter motion that another 2 Newton force is trying to cause in the opposite direction. So we expect this 2 Newton to completely counteract this 2 Newton, such that that object now remains still, as if there's no object, there's no force on it. There are forces on it, but the resultant of the forces is equal to 0. If you check the resultant of 2 and 2, from what we did on that resultant, you will discover that it is 0. So it is as if this object is not even acted upon by any force. When an object does not have a force on it, it does not move because its acceleration is 0. It will either not move at all, or if it has to move, it will move with constant velocity. Under that condition, we say that the object is in a condition of translational equilibrium. It is moving or it is at rest. It is moving or it is at rest under a net force of 0. The resultant force on it is 0. It does not have a resultant force on it that is causing motion. So it is. Now, it is possible now that the object does not move, but it will still rotate. A very good example of an object that rotates without moving translationally from one point to another is a fan. If you have a fan that is rotating on the ceiling, the fan is not moving from one point to another, but I hope you know it is actually rotating. So it is possible for an object not to translate, not to undergo translational motion, but to be rotating. Why? Because you have two things that are a little bit different that are required for the two. It is moment that is required for rotation. It is a force, a net force that is required for motion. It is the net force that is required for motion. It is moment, a net moment that is required for rotation. When you see an object rotating, turning, it means that there is a moment on it that is making it turn. If you see an object moving, most likely there's a force on it that is making it move. So if an object is having rotational motion, there is a moment that is causing that rotation, that is causing that turning. When an object is not rotating, it either means there's no moment on it or the net moment on it is zero. When I say net moment on it is zero, if the force or the moments that are trying to cause a clockwise movement have been counterbalanced with a moment that is with the moments that are trying to cause anti-clockwise motion or anti-clockwise turning, then we'll say that there's equilibrium, there's rotational equilibrium. If an object is undergoing translational motion, if an object is undergoing translational motion, the most likely thing is that there's a force on it that is making it to move. So if an object is not moving at all, it means that the forces on it, the net force on it is equal to zero. I'll go over that again. Moment is necessary for a rotational motion. So when an object is rotating, there's a moment that is acting on it. When an object is therefore not rotating, it means the net moment on it is equal to zero. Force is required for a translational motion. When an object is moving on a straight line, there's a force on it that is making it to move on a straight line. When the net force on it is equal to zero, then it won't move at all. So when an object is such that it's not moving and it is also not rotating, it means that, number one, there's no net moment on it. That's why it's not rotating. It also means that there's no net force on it. That is why it is not moving. Again, as I said, force is required for an object to move from one point to another. For an object to move from one point to another, that's translation. A force is required. So if you see an object that is moving from one point to another, most likely there's a force on it. For an object to rotate, moment is required for an object to rotate. When you see an object rotating, there's a moment that is making it to rotate in that direction. So therefore, if an object does not have this, if an object is not moving, it means that there's no force or there's no net force on it. There's no force on it, there's no net force on it. So the net force on it will be equal to zero. If an object is not rotating, it means there's no net moment on it, or the moment on it is equal to zero. When this is achieved, we'll say that the object is experiencing equilibrium. It's experiencing equilibrium. And in such case, you will discover that the object is not moving and it's also not rotating. When you see an object that is particularly static, that object is experiencing equilibrium. But that is not, those are not the set of, static objects are not the only set of objects that experience equilibrium. We are still going to get to it. When we get to Newton's law, we'll try to expand the definition. But I want to keep it that simple. When you see an object that is not moving and is not rotating, it is experiencing equilibrium. And why is an object experiencing equilibrium? It doesn't mean that there's no force on it. There can be forces acting on it. But the sum total of all of the forces, the sum total of the effect of all of the forces amount to zero. Probably there are the total forces that you have in one particular direction is equal to the total forces that you have in the opposite direction, such that the effect of those forces completely counteract each other. Then it looks as if there are no forces on it. The same thing for moment. When the total moment in the clockwise direction is equal to the total moment in the anti-clockwise direction, so the object will not even rotate at all because there's nowhere it wants to turn to, clockwisely as completely counterbalanced anti-clockwisely. So when the sum total of moment on an object is equal to zero, then the object is experiencing equilibrium. Let's take a cut a little and try to see the different types of forces that can act on an object. Number one, we have some forces that are called collinear forces. Collinear forces. Collinear forces are forces that act on the same line or on the same axis. When forces are collinear, it means they act on the same line or they act on the same axis. If I have an object, like I said earlier, I have a 2 Newton force acting to the east, another 2 Newton force acting to the west. These forces are collinear because they act on the same line. Linear is from the word line. So collinear, it means they act on the same line. So therefore, if they do not act on the same line, I can call them non-collinear forces. If, for example, I have an object, 2 Newton is acting in one direction, 3 Newton is acting in this other direction. These 2 and 3 are clearly not on the same line, so they are not collinear. Another one, coplanar. Coplanar forces. What are coplanar forces? Coplanar forces are forces that act on the same plane. Planar is from the word plane. Forces that act on the same plane are called coplanar forces. This is a plane. A plane is the intersection of 2 axes. The board is a plane. If I can represent forces on the board in any direction, as long as I can put them on the board, then they are coplanar forces. They are all coplanar forces. But the moment you have one that is joining them that I cannot represent on the board, for example, if I have a force that goes into the board, that cannot be put on the board. Or if I have a force that is coming out of the board, that can also not be put on the board. So that one makes it non-coplanar. But as long as I can represent all of them on the board, then they are all coplanar forces. Now, there are also forces that will call concurrent forces. Concurrent forces are forces whose line of action meets at a point. When their line of action meets at a point, they are concurrent. For example, if I have an object, there's a force, there's another force, and there's another force, such that when I extend the 3 of them, they meet at one single point on the object. Then, if this is A, this is B, this is C, because A, B, C meet at the same point, I will say that the 3 of them are concurrent forces. So we are going to gradually see how the knowledge of collinear, coplanar, and concurrent forces can affect our study of equilibrium. So let's go back to what we're discussing under equilibrium. For an object, therefore, to be in equilibrium, it means that the resultant forces on the object or the resultant force on the object must be equal to 0. For an object to also be in equilibrium, it means that the resultant moment on the object must also be equal to 0. Why did I say so? I said that if the object is not moving, it means the forces on it 0. If it's not rotating, it means the moment on it is 0, because it is the moment that makes it to rotate and it is the force that makes it to move. So when the force is 0, it does not move. When the moment is 0, it does not rotate. Let's keep the definition that simple. Like I said earlier, when we get to Newton's law, we are going to expand on that. So I can now ask you that an object is acted upon by several coplanar forces. An object is acted upon by several coplanar forces. Tell me the condition under which you feel that despite all of these forces, this object will still be in equilibrium. I can ask you to tell me the condition under which, despite the action of all of these forces, this object will still be in equilibrium. What I'm asking you to tell me at that time is the condition necessary for an object acted upon by coplanar forces to be in equilibrium. What I want you to tell me at that point, as I said earlier, is the condition under which an object acted upon by parallel coplanar forces or coplanar forces will still be in equilibrium. And there are just 2. I have explained those 2. We are now just going to put them in very technical terms. Number 1, the condition necessary for an object to be acted upon by coplanar forces to be in equilibrium. Number 1 is that the sum of forces in any given direction on the object must be equal to the sum of forces in the opposite direction. The sum of all forces acting in a particular direction must be equal to the sum of forces acting in the opposite direction. If there are so many forces on an object and the object is still in equilibrium, the simple meaning is the forces have completely counteract they have completely counteract each other. They have completely counterbalance each other, such that those that are trying to move it in a particular direction have the same magnitude as those that are trying to move it in the opposite direction. So in that case, both effects are defeated because all forces just cancel out each other. So a way to put that is one of the conditions necessary for an object acted upon by parallel coplanar forces is that the sum of forces in any given direction on that object must be equal to the sum of forces in the opposite direction. The sum of forces in any given direction must be equal to the sum of forces in the opposite direction. If we have 10 Newton moving it up and it's in equilibrium, it is because there's another 10 Newton that is moving it down. If you have 50 Newton moving it to the left, to the right, it means there will be 50 Newton that will also be moving it to the left. So that is the only thing that can make it to be in equilibrium. The moment there is an imbalance between the forces in one direction and the forces in the opposite direction, that object is going to move, and it's going to move in the direction of the force that is greater. And number two, the sum of clockwise turning moment of all forces on the object must also be equal to the sum of anti-clockwise turning moment of all forces on the object. So it means that if an object is to be in equilibrium, forces in one direction must be equal to forces in the opposite direction, while the moment, clockwise moment on the object must be equal to the anti-clockwise moment on the object. There are so many things that can be done with the knowledge of these two conditions that have been stated. We're going to try to attempt to solve some questions based on the knowledge of equilibrium and what is required for an object to be in equilibrium. But first, let me give you a series of terminologies that can be used in this aspect of learning so that when we start to meet them, you will understand exactly what you are expected to do. Number one is usually under this topic we work with materials like beam, rod, plank, etc. We are to represent them simply with a line. We are to represent them with a line. The question will naturally tell us how to place them. An horizontal rod, they will place it like this. A vertical plank, they will place it vertical with a line. Now, number two, we can be told that the object is uniform. We can be told that the object is uniform. If it is uniform, it means that the weight of that object is at the middle. It means that the weight of that object is at a midpoint on the object. For example, if the plank is 10 meters long, usually I will represent it with a line. I'll put 0 at one end and I'll put 10 at the other end. Then I'll come to the middle, that is where my 5 is, and I will show the weight. Remember that I said that we always show weight with a vertical line that is acting downward. We show weight with a line, a vertical line that is acting downward. If the plank is 10 meters, I'll call one end 0, I'll call the other end 10, and I'll come to the middle. The middle of 10 should be 5, and I will indicate the weight if it is uniform. Uniform means that the weight of that object is in the middle. If it is 8, it means the midpoint will be 4, and that is where I'm going to show the weight. If it is 6, it means the midpoint of that object will be 3, and that is where I'm going to show the weight. I can also be told that it is light, that the object is light. If the object is light, light means, another word they can use instead of light is, it is weightless. If the object is weightless, it simply means that it has no weight. If you are told that the object you are working with, the plank you are working with, is weightless, you don't even need to show the weight. There are times you will now see negating words like The object is uniform and it is weightless. Being weightless, it makes the meaning of uniform irrelevant because uniform means the weight is at the middle. But this time, it is even light. That means it does not have weight. What you are told to put at the middle does not even exist. So, your uniform, when it is light and it is weightless, if it is uniform, it means the weight is at the middle. Now, please always pay attention to that. If an object is not uniform, then it is non-uniform. If it is non-uniform, in that case, they must tell you where to place the weight. If it is non-uniform, then they must tell you where to place the weight. If it is not uniform, they must tell you where to place the weight. And one simple language by which they can use to tell you where to place the weight is by giving you the center of gravity of the object. Center of gravity of an object is a point on the object where the weight of the object appears to act, irrespective of the position of the object. All objects have a center of gravity, and the center of gravity is a point on that object where is weight, the resultant weight, where the whole of the weight of that object appears to act or appears to be, irrespective of the position of the object. If, for example, the center of an object is at point 3, whether the object is placed slanted, is placed horizontal, is placed vertical, is placed in the other form inclined, it means that it is still at that same point 3 that the weight must be. His weight must be at that point 3. His weight must be at that point 3. His weight must be at that point 3. So the center of gravity of an object is the point on the object where the resultant weight of an object appears to be concentrated or appears to act. And that is it. So if an object is uniform, definitely its center of gravity is at the middle. But if an object is non-uniform, then they must tell you where to place the center of gravity. Is it going to be at the middle, or will it be at some distance closer to the end, closer to one end than the other? For example, I can give you a 5-meter long beam, whose center of gravity is 2 meters from one end, 2 meters from one end. In this case, it means that the center of gravity of that object is closer to one end than the other, probably because this happens for materials where the object has more of such material to one side. For example, if you have a plank that is cut in this form, then we expect the center of gravity not to be at the middle because there seems to be more material on one end than at the other end. The material tapered to one end. So in this case, we expect the center of gravity to be closer to the end where we have more of such material. So that is it. So we can have an object whose center of gravity is at the middle, and we can have several other objects whose center of gravity will not be at the middle. In that case, they are not uniform. Now, we can have a plank that has its own weight, probably at the middle or not. And we can also now add additional load to that object at several points. If you add additional load to that object at several points, each of those loads will also have their own individual weights. It will have their individual weights, and we'll still show them with the arrow that we always use to show the weight of an object. Remember, I said that the weight of an object is always shown with a vertical line that is acting straight down. The weight of an object is always acting vertically down, irrespective of the position of the object. So whether the object is placed slanted, is placed horizontal, or is placed vertical, any weight that is on it, or even its own weight, must act vertically down. And that is what we are going to have here. So if additional weights are placed on a plank or rod, this is how we show them. We'll put the weights and we'll have their weight shown with a vertical line that is acting straight down. Now, an object or a plank or a beam can also be supported. Of course, if an object is not supported, we expect that that object will fall off. If all objects, when placed in air, will naturally fall due to the action of its weight. I just told you how the weight wants an object to move. The weight wants an object to fall vertically down. When we place an object in mid-air, the object will naturally fall due to the action of its weight. The weight of an object wants it to fall because the weight is acting down. So if you don't want an object to fall, by the action of his weight, then in that case you must support it. There are different types of support that you can give to an object. You can place stress tools or stand directly under the object. That is one way. You can place stress tools or stand directly under the object. You can also tie rope around some point on the object and hang it at a point that is vertically above it. You can do something like that too. So in both cases, what you are trying to do is, since you know that the object wants to fall by the action of its weight, you are now trying to exert an upward force to prevent it from falling. The name of that upward force is called normal reaction. If it is supported from under, if it is supported by stress tools or even humans, if for example this were to be a long plank and you have two men trying to carry it on their head, then they are exerting a normal reaction on it. A normal reaction is a force of support and it is always acting away from the object. Here too, there's a support, but if these are ropes or strings or wires that have been used to attach the plank to a point directly above it, then there's an upward force, or there are upward forces on it, and the name of these upward forces are tensions. They are called tensions. If we have two ropes, we have two tensions. If we have only one, we have only one tension. If there are more than one rope, we have two tensions, three tensions. It's even possible that we are told that both tensions are equal. Then in that case, we represent them with TT. If they are different, we represent one with T1 and the other one with T2. So things can be supported this way, or they can also be supported this way. Either of the two is still correct. Now, what we'll do is to try to take a question, or if we have more time, we'll take more questions to explain this fact. We are told here that a uniform rod 8 meters long, weighing 5 kilograms, is supported horizontally by two vertical parallel strings at P and Q, and at distances 2 meters, 6 meters from one end. Weights of 1 kilogram, 1.5 kilogram, and 2 kilogram are attached at distances of 1 meters, 5 meters, and 7 meters, respectively, from the same end. Find the tension in each vertical string. I'll go over the question again. A uniform rod 8 meters long, weighing 5 kilograms, is supported horizontally by two vertical parallel strings at P and Q, and at distances of 2 meters and 6 meters from one end. Weights of 1 kilogram, 1.5 kilogram, and 2 kilogram are attached at distances of 1 meters, 5 meters, and 7 meters respectively from the same end. Find the tension in each vertical string. So we'll start. We are told that we have a uniform rod. There's a uniform rod. That rod has a length of 8 meters. We are told that it is 8 meters long. My way of showing the distance, I'll put 0 on one end, I'll put 4 on the other. I will come to the middle, indicate it, and I will show the weight. Since this question is telling me that the object has a weight and it is uniform, because it is uniform, it means I must show the weight at the middle. A uniform rod 8 meters long, weighing 5 kilograms. The weight is 5 kilograms. The weight is given to be 5 kilograms. Is supported horizontally, is placed horizontally by two vertical parallel strings at P and Q. I just told you how you can use string to support an object. So the string is placed at one point, is attached to a point directly above it. Another string is placed at another point and is attached to a point directly above it. It's supported by two vertical parallel strings at P and Q. One is at P, one is at Q. We'll move on. And at distances 2 meters and 6 meters from one end. One is placed at 2 meters from one end. The other is placed at 6 meters from that same end. So one is placed, I will take this as my end. I will say that P is placed at 2 meters from that end, while Q is placed at 6 meters from that same end. So we can continue. We are told that weights of 1, 1.5, and 2 are attached at distances 1 meters, 5 meters, and 7 meters respectively from that same end. So we'll come to that same end. 1 meters from that end, we are placing a weight. 5 meters from that end, we are placing another weight. And 7 meters from that end, we are placing another weight. Everything is measured from one end. The question also stated that they are all placed from the same end. So what is the weight that is placed at 1 meters? It is 1 kilogram that is placed there. What do we have placed at 5 meters? At 5 meters, we are placing 1.5 kilogram. 5 meters, we are placing 1.5 kilogram. And what do we have placed at 7 meters? At 7 meters, we are placing 2 kilogram. At 7 meters, we are placing 2 kilogram. So we are asked to find the tension in each vertical string. So this string will have a tension, I said it earlier. This string will also have another tension, said it earlier. We are not told that both of them are different, that they are the same, sorry. So I'm going to denote them as T1 and T2. If they are not the same, by the time I solve it, I'll get the same value for them. Now, these are the things that we are able to come up with. Your understanding of this topic must come from the fact that you must be able to produce a correct diagram anytime you are solving the question. If in my interpretation of this question, one part of what I have shown has not been correctly shown, then ultimately I cannot get the question. You must show all parts correctly. You must read through the question for as long as it takes for you to be able to bring up the right diagram for you to solve with. Now I want to find T1 and T2. The object is in equilibrium. We are told that it is supported horizontally. That means it's at equilibrium. So if it is supported horizontally and it's in equilibrium, what we need to do is to evoke the two conditions for an object that is experiencing equilibrium despite the fact that it is acted upon by forces. Now, one other thing I want you to pay attention to is the fact that my weights, in this case, I have decided to leave them in kilogram. I can leave my weight in kilogram. It is possible that I leave them in kilogram. Why? I can also leave my weight in Newton. The only thing is, whatever unit you want to put your weight in, your weight is a force. The most appropriate unit for your weight should be Newton. But you can also leave them in kilogram because it is allowable. You can easily convert your answer from kilogram. You can easily convert from kilogram straight to Newton, and you can convert from Newton back to kilogram. But the only thing is, any unit of the two that you have decided to use, that must be the unit that you are going to use throughout your question. For example, all forces, since I have chosen to represent my weight with kilogram, every other weight must be in kilogram, and the tension, which are forces that I've been asked to get to, I must get them in kilogram. There must not be a situation where I'm going to be mixing kilogram with Newton. It is not possible. Everything must be in the same unit. If I decide to change this 5 kilogram to Newton, then it means I must change 1 kilogram to Newton, 1.5 kilogram to Newton, 2 kilogram to Newton, and the other forces in the question, I'm going to get them with in Newton. Another thing I would like to say is, please note the direction of my tension. Tension is always, when you have an object and you are supporting it with a rope, please note that you usually cannot support with a rope downward because the object naturally wants to go down. So you are supporting with a rope upward, and the direction of that tension must be vertically upward, must be upward. It cannot be downward again. Because the tension is preventing this object from falling. Whatever is going to prevent an object from falling must be up, because falling is down. Now, I can solve the question. The first thing about the question is I'll make sure that there's nothing that I've not shown, and clearly there's nothing I've not shown. The first condition of equilibrium is the sum of forces in one direction must be equal to the sum of forces in the opposite direction. All the forces shown in this question are just either upward or downward. T1 and T2 are upward. 1, 1.5, 2, and 5 kilogram are downward forces. So I can decide to say that the sum of forces in one direction, if I take upward to be one direction, then I can take downward to be the other direction. Upward forces T1 plus T2 must be equal to downward forces 1 plus 5, 1 plus 5 plus 1.5 plus 2. If I do that, I'm going to have T1 plus T2 is equal to 1 plus 5 is 6, plus 1.5 is 7.5, plus 2 is 9.5. So I've been able to get the first equation. The second equation now will come from the second condition of equilibrium. Don't forget that the second condition for equilibrium is that the sum of clockwise moments must be equal to the sum of anticlockwise moments about any point on the object. The sum of clockwise moments must be equal to the sum of anticlockwise moments about any point on the object. The sum of clockwise moment of all forces, because moment is found for forces about a point. The sum of clockwise moment of all forces about any point on the object must be equal to the sum of anticlockwise moment of all forces about the same point on the object. So I'm going to find the moment of all of these forces. I am going to write out those ones that I feel are clockwise and those ones that I feel like are anticlockwise. Then because the object is in equilibrium, it means that the clockwise moment must be equal to they've completely balanced the anticlockwise moment. So to do that, I will first list out all the forces from 1, T1, 5, 1.5, T2, and 2. I've been able to list all the forces in the order in which they appear in the question. 1, T1, 5, 1.5, T2, and 2. Then I will multiply them with the perpendicular distance to find the moment. I want to find the moment. Before you find the moment, you must pick a point about which you want to find the moment. You must pick a point about which you want to find or determine the moment. It is very, very necessary. I have different points on the object. Anywhere I have a force is a point. The ends are also points. I can pick the point 0. I can pick the point 8. I can pick the point where 1 is. I can pick the point where the P point, where T1 is. I can pick point 4 where 5 is. I can pick point 5 where 1.5 is, and so on and so forth. So before you find moment is force times distance, you must know the point to which you are going to be determining the distance for each of the forces. Here, I want to pick the point 0. Please, taking moment about point, taking moment, tell them that you are taking moment about O, about O. If you are taking moment about O, we can now move on. Clearly, if I want to move on from there, I will now need to get the distance of each of these to point O. Now, the distance of 1 to point O is 1 because 1 is placed at 1 and the distance of 1 to 0 is 1. So I'm multiplying 1 by 1 and that should give me 1. The distance of T1 to point O is 2 because T1 is placed at point 2, is placed at 2 meters. So distance of 2 meters to O should be 2. That is why it is easy to take moment about O. It is easy to take moment about 0 points. Whatever those values are, that is what you are just going to use. 5, the distance of 5 to O is 4. So 5 times 4, that is 20. So I'll just continue in that order. 1.5 to O is 5. 1.5 times 5 is 7.5. Distance of T2 to O is 6. That will be 62. The distance of 2 to O is 7. If you multiply it, you get 14. We are not done. We need to know for each of these moments that we have calculated, which one of them is clockwise and which one of them is anti-clockwise. It is very, very necessary that we decide. And how do we do that? Since we are taking moments about point O, we assume we are holding this plank, this 8-meter plank. We assume we are holding it at O, and we are exerting each of these forces at the respective point that we have placed them. If I exert one at this point, if I hold the plank at this point and I exert one in this same direction, what direction will it turn? It will turn clockwisely. So the first point is clockwise. If I hold it still at same point O and I decide to exert a T1 up in that same direction, it will move this plank anti-clockwise. Anti-clockwise, I'll call it AC. So if we continue in that order and check, we can even use our eye to check to see which one will be clockwise and which one will be anti-clockwise. If I hold it at point O and I exert a 5 kilogram force, it will be clockwise. 1.5 will be clockwise. T2 will be anti-clockwise, and 2 will be clockwise. Please note once again that the unit of moment is Newton meters, because the force must be in Newton, the distance must be in meters. I've only used kilogram because kilogram is the predominant unit in this question. I could have easily converted them to Newton too, and I'll still get the same answer. The only thing I just told you earlier is what you must stick to. If you have decided to work in kilogram, it means every one of your force that you are going to use in this question must also be in kilogram. If you have decided to work in Newton, every single one of the forces that you are going to use in this question must also be in Newton. Do not mix units. Don't solve a question that has kilogram and Newton together. It's either you use kilogram all through or you use Newton all through. I've decided to use kilogram all through, but I could have easily converted them to Newton by multiplying each of these values by 10. So the second condition of equilibrium is that for this object to also be in equilibrium, the sum of clockwise moments must also be equal to the sum of anti-clockwise moments. The clockwise moments in these questions are 1, 20, 7.5, and 14. So I'm going to put them all on one side. 1 plus 20 plus 7.5 plus 14 must be equal to, I'll put the others on the opposite side. The others that will be on the opposite sides are 2T1 and 6T2, because those ones are anti-clockwise moments. So I'm going to have 2T1 plus 6T2, and we are going to try to solve it. So I'll add 1 to 20, that's 21. 21 plus 7.5 is 28.5. 28.5 plus 14. 5 plus 14 should give us 42.5. 42.5 is now equal to 2T1 plus 6T2. I can solve the equation 1. I can call the equation that I got earlier equation 1, and this second equation I can call it equation 2. All I now need to do is to solve equation 1 and 2 simultaneously to be able to solve the answer. So I can make T1 the subject. I can make T1 the subject. In the first equation, T1 must be equal to 9.5 minus T2. If that is the case, I can now substitute it in the second equation. That will be 42.5 is equal to 2. Instead of T1, I will substitute T9.5 minus T2 close bracket plus 6T2. So I should have 42.5, 19. So I'll use 2 to multiply the two items in the bracket. That will be 19 minus 2T2 plus 6T2. That should be 42.5 minus 19 is equal to 4T2. And that should be 4T2 must be equal to 42.5 minus 19. Minus 19 should give us 23.5. 23.5. So my T2 should therefore be equal to 23.5 divided by 4. My T2 must be 23.5 divided by 4. which is 5.875. If T2 is 5.875 kilogram, because I told you that kilogram is the predominant unit in this question, I can easily find T1. And I said T1 from here is 9.5 minus T2. T1 is equal to 9.5 minus T2. If that is the case, that would be 9.5 minus 5.875. And that should be 9.5 minus 5.875 should be 3.625 kilogram. So my T1 and my T2 have been completely calculated, and that brings us to the end of this question. But we are still going to now solve for more concepts under equilibrium. So we are going to take another example on concurrent forces. Remember I said earlier that concurrent forces are forces whose line of action meets at a point. Concurrent forces are forces whose line of action meets at a point, and usually concurrent forces helps to keep an object in equilibrium. A very good example of a question on concurrent forces is something like this. So there are so many examples on concurrent forces in JAMB questions, amongst even in WAEC and A-level questions. So we can try to look at this question. They said, if the system of forces shown in the diagram is in equilibrium, the tension T2 is equal to, what will be the value of T2? What will be the value of T2? We have an object of mass 5 kilogram, and there's a point where the three forces are meeting. Where are the three forces? I hope you can see that there's a force here, T1. There's another force here, T2. There's a third force, and that force has to be the weight of this object. When you attach this object to a system like this, I hope you know that the weight of the object is always acting vertically downward. I can replace the object with its weight. So this time I wish to work with Newton. If you want to work with Newton, you just multiply your mass, your value in mass by acceleration due to gravity, which is 10. So if I multiply 5 by 10, I will have 50, and that will be 50 Newton. So now I have three forces on the board. There's a T1, there's a T2, there's a 50 Newton, and we can easily use this to solve for T1 and T2. Mind you, in starting this question, I told you that if any force is inclined, the very first thing you must try to do is to resolve it. When you resolve it, you have a proper idea and understanding of what the question looks like. You resolve it from its point of origin. The point of origin of T1. T2 is horizontal, I don't have any problem with it. 50 is vertical, I don't have any problem with it. But T1 is inclined. I have to resolve it from the point of origin. So from this point, I will do the vertical, and I will do the horizontal. When I do that, I can now resolve it. But this time, remember that in resolving, I need the angle that it is making with either my horizontal component or my vertical component. None of that is given. But that is when I will now see that there's a 30-degree angle that has been given to the vertical. So what I will just do, since vertical axis, any vertical axis are always parallel to each other. If this is a vertical axis, any other vertical axis that is drawn to it must be parallel to it. So if this is parallel to this, it means I can use the alternate angle in mathematics. If I do that, I can bring that 30 to this point, 30 degrees. When I bring 30 degrees to that point, then I can clean it off from here. In fact, I don't need the whole of this anymore. If I remove that, then I can now resolve my T1. If I resolve my T1, remember I said the component beside the angle is cos. This becomes T1 cos 30 degrees, and this becomes T1 sine 30 degrees. Once resolved, I can remove the original vector. So if it is in equilibrium, remember what I told you. The sum of forces in one direction must be equal to the sum of forces in the opposite direction. So one direction is upward. The sum of forces in the upward, the only force that is upward is T1 cos 30. If this is in equilibrium, if the whole of this system is in equilibrium, it must be equal to the forces, the sum of forces downward, and there's only one force downward. So I can use, it means T1 cos 30 will be equal to 50. So now, what is T1? T1 must be equal to 50 all over cos 30. But T1 is not what they want me to find. what they want me to find is actually T2. T2 will come from the next equation of equilibrium. The sum of forces in one direction must be equal to the sum of forces in the opposite direction. I've said that the forces or the force that is acting upward must be equal to the force that is acting downward if the system is in equilibrium. Also, the force that is acting to the right must also be equal to the force that is acting to the left. If that is the case, I can easily say that T2 must be equal to T1 sine 30. If that is the case, I can now say that my T2 must be equal to, I've been able to get an equation for T1. T1 is 50 over cos 30. If T1 is 50 over cos 30, I'm multiplying it by sine 30 now. If I multiply it by sine 30, I should have something that looks like this. So upon continuous evaluation, I can now have 50 sine 30 all over cos 30. If that is the case, I can say that my T2 must be equal to 50 cos 30 all over sine 30. It's not compulsory, you know that cos 30 over sine 30 over cos 30 is tan 30. It's not compulsory. You can just put in the values. If I have to put in the values, it will be 50 multiplied by sine 30 is 0.5, while cos 30 is 0.866. But mathematically, if you know that cos sine 30 over cos 30 is tan 30, then you can easily continue that evaluation. That will be 50 multiplied by tan 30, in this case, is either root 3 over 3 or 0.577. If you want to express it in short form, it is root 3 over 3, which makes it 50 root 3 all over 3. Or if you want to express it in decimal, depending on what form the options are presented in the question, 50 times 0.577, we have 28.87 Newton. So that is the case here. And with that, we have been able to solve questions on concurrent forces. There are more questions on concurrent forces that we can get. In fact, I remember that there's a particular question from JAMB where we were told that two men were carrying a load. Each of them was carrying it with handle that is next to him, such that each of those handle is making an angle of 60 degrees with the horizontal. The man on this side is holding the handle that is next to him. The man on this side is also holding the handle that is next to him. Both handles of the bag or the load are making an angle of 60 degrees to the vertical. The weight of the load is given, I think is 162 Newton. The question is that we should find the tension on each arm. The tension on each arm. I'm going to call this one T1. I'll call this one T2. Number one thing I must tell you is this. If the two vectors are inclined at the same angle, then they must be the same. Because the two of them are inclined at 60, 60, then T1 and T2 must be the same. If they are to be different, then the angle of inclination too must be different. If they are the same, then the angle of inclination must be the same. If we are given the angle of inclination to be the same, is an hint that the tensions are also the same. So, and if you have a problem like this, the necessary thing that you must do anytime your forces are inclined is to resolve them. That's the only thing that once you resolve, you understand the question better. If I resolve this, and I resolve this into vertical and horizontal, then I should be able to get the question. Remember that when you resolve, this becomes T cos 60, and this also becomes T cos 60. This becomes T sine 60, and this also becomes T sine 60. If that is the case, we can clean the item within the triangle. We can clean the force that we are resolving. because we don't need it anymore. Now we can invoke the condition of equilibrium. The sum of forces in one direction must be equal to the sum of forces in the opposite direction. We can do that for the horizontal. That means T sine 60 must be equal to T sine 60. We cannot get anything from there. But we can also do that for the vertical. That means the sum of forces upward must be equal to the sum of forces downward. In that case, it means T cos 60 plus another T cos 60, because we have 2T cos 60 up, must be equal to 162. So when we add this together, we have 2T cos 60. It should be 162. That will be T. 2 times T multiplied by cos 60 is 0.5 is equal to 162. If you multiply 0.5 by 2, I think we are going to have 1. So it simply means that T is equal to 162 Newton. That is another question on concurrent forces. And there are so many other ones that you can get. I want to advise that we try out so many other questions that we have on concurrent forces from our various textbooks and past questions. We are going to move to polygon law of vectors. Polygon law of vectors is also going to be studied under equilibrium, and it is a law that helps us to understand concurrent forces better. It gives us another representation by which we can use to solve concurrent forces. Generally, what the law is trying to tell us is if we have a number of vectors that are acting together to keep an object in equilibrium, then they can be represented by the side of a polygon that is taken in order, by the side of a polygon that is taken in order. For example, if we have 4 forces that are acting to keep this object in equilibrium, then the 4 of them can be represented by the sides of a quadrilateral, if I take it in order. If we have 3 forces that are acting to keep an object in equilibrium, they can be represented by the sides of a triangle taken in order. So we can represent a number of vectors that are acting to keep an object in equilibrium by the side of a polygon that has the same number of sides as the number of vectors that we have in the question. If they are starting from 3, we have 3 vectors that are acting to keep an object in equilibrium, then they can be represented by the sides of a triangle taken in order. If I have 4 forces acting to keep an object in equilibrium, then they can be represented by the size of a quadrilateral taken in order. If I have 5 forces acting to keep an object in equilibrium, then I can represent all 5 by the size of a pentagon taken in order. If I have 6 forces acting to keep an object in equilibrium, then they can be represented by the sides of an hexagon taken in order. So if we now want a general application, the general law that brings together the very first one, because it has 3 forces, we said is a triangular vector. This one quadrilateral law of vector. This one is pentagonal law of vector. This is hexagonal law of vector. If we now want to bring all of them together under a single law, we'll call that law a polygon law of vector. And polygon law of vector states that if n number of vectors, n number of vectors, n now represent anything from 3 to 4 to 5 to 6 to 7, act to keep an object in equilibrium, then those forces can be represented by the size of an n-sided polygon taken in order. It can be represented by the size of an n-sided polygon taken in order. If n number of vectors act to keep an object in equilibrium, then they can be represented by the sides of an n-sided polygon taken in order. That simple law can be used to solve a lot of things. I'm going to apply the triangle law of vector. To solving the question that we had before. Remember, we had a T1, we had a T2, we had a 1. T1 was inclined at an angle of 30 degrees. Then we have a force, which is the weight, a force of 50 Newton. We initially solve this question by doing what we call, by resolving T1. But if you don't want to use T1, you can, since the three of them are acting to keep the object in equilibrium, then we can represent them by the size of a triangle taken in order. What do we mean by taking in order? You start with any one. You can turn the question to a triangle. Start from any one. I can start from 50. If I start from 50, the way 50 is downward. At the end of that, my 50, I'm going to put another vector, still from this shape. I'm going to put T2. I can put T2. I can put T1. If I want to put T1, T1 must be in its original direction. You are going to arrange the three of them to make a triangle without altering the direction of each of the vectors. So I'm going to put T2. If I put T2 in this direction, and that is exactly how T2 is. It means the space available must be such that will allow T1 to fit in perfectly. And that is exactly how T1 looks like. That is exactly how T1 looks like. So it clearly shows that this is a right angle triangle. It clearly shows the angle 30 that T1 is making with the vertical. I can still put that angle here. The angle that T1 is making with the vertical, this is the angle. This angle is 30. This is T1. This is the vertical angle. This is the vertical. This 50 is on the vertical direction. So from this triangle, clearly I can find T1 and I can find T2 using SOHCAHTOA. I know the adjacent of 30 to be 50. I want to find the opposite, T2, or the hypotenuse, T1. I can find either of the two from that triangle by simply applying SOHCAHTOA. If I do, for example, tan 30, if I do tan 30 is opposite, which is T2, all over adjacent, which is 50. So clearly T2 becomes, if I cross multiply, it becomes 50 tan 30. And that was exactly the same thing that we had before. Another aspect of equilibrium, another method that can also be used to solve concurrent forces is what we call Lami's theorem. Lami's theorem. Lami's theorem can be used specifically to solve problems where three forces act to keep an object in equilibrium. Where three forces act to keep an object in equilibrium. If I have T1, the way it is shown on the board, T1, and I have T2, the way it is also shown on the board, then I have 50, the way it is shown on the board. If I have it and I want to use Lami's theorem, all I just need for Lami is to know the angle between any pair of vectors from that question. Any pair of vector between 50 and T2, I don't have any problem. This should be 90 degrees because 50 is vertical, T2 is horizontal. So the angle between an horizontal direction and a vertical direction is 90 degrees. Now I need to know the angle between T2 and T1. I also need to know the angle between T1 and 50. And how will I get that? I said earlier that we can use Z angle. We can draw a vertical direction here. We can use Z angle to transmit this 30 to this point. This place becomes 30. If that is 30, from here to here should be 90. So the angle between T2 and T1 should be 90 plus 30, and that is 120 degrees. If that is the case, then I can now also say that the angle between T1 and 50 will be known, because the angle at a point, the three of them forms angle around the point. Angle at a point is 360. A part of that 360 is already 90. Another part is 120. If I add them together, that is 210. If I subtract from 360, I'll get 150. So what Lami, if I know the angle between all pairs of vectors, what Lami is trying to tell us is any vector that you take, T1, all over the sine of the other two. The sine of, if I take T1, I will put the ratio of a vector to the sine of the angle between the other two vectors is a constant. That means T1 all over sine 90. You know 90 is the angle between T2 and 50. It must be equal to T2 all over the sine of the angle between the other two. The other two in this case is T1 and 50. That is 150 is equal to 50 all over sine of the angle between the other two. The other two in this case is T1 and T2, and the answer is 120. So with this, I can easily solve whatever I need by picking any two. I can pick this, and I will outrightly get my T2. Since I know this, and I know this. So Lami's theorem can be specifically used for concurrent forces that are just three, holding an object in equilibrium. So if I have three forces that are holding an object in equilibrium, I can use Lami's theorem as much as I can use triangle of vector, and I can use resolution of vector to solve it. The last part that we are just going to look at is the aspect of a couple. A couple is a pair of equal, parallel, oppositely directed forces that do not have the same line of action. They do not have the same line of action. It must be the couple. When we say couple, they must be a pair. Must be a pair of vectors or forces that are equal in magnitude. They must be parallel, they must be opposite, but they must not have the same line of action. For example, if I have a plank, let me draw 5 different things. If we have a plank that is acted upon by 3 Newton and another that is 4. If we have one that is 3 Newton and another that is also 3. If we have one that is 3 and another 3. If you have one that is 3 and it's also 3 on this other side, then we are asked to determine which one is a couple of the 4 setup. This is not a couple because for them to be coupled, they must be equal in magnitude. We must have a pair and they must be equal in magnitude. The pair here are not equal in magnitude. This is 3, this is 4. So this is clearly not a couple. This is also not a couple because here they are not parallel, and couples must be parallel. 3 and 3 here are not parallel, so this is not a couple. This is also not a couple. Why? They do not have the same line of action. They have the same line of action. For couples, they must not have the same line of action. So this cannot be referred to as a couple because they are attached, they are joined on the same line. That means they have the same line of action. This is the one having what others do not have. They are equal, they are parallel, they are oppositely directed, and they do not have the same line of action. That makes them a couple. So we can be asked to find the moment of a couple. We can be asked to find the moment of a couple. A very good example of a place where we practically use a couple is if when you try to open your tap. If you try to open your tap, you have a tap. In opening a tap, you must exert a downward force on one end of the tap and an upward force on another end. Both are actually very equal, so we call this a couple. When you drive, holding this wheel, the steering wheel of the car, requires a couple. While one end brings down the wheel, the other end raises it up, and both of them are exerting equal magnitude, so it is also a couple. The moment of a couple can be found. It is called torque. And how do we find the moment of a couple? It is the product of one of the forces multiplied by the perpendicular distance between them. This time we don't need a point. It is a product of one of the forces. We know there are 2 forces that makes a couple. The product of one of them multiplied by the perpendicular distance between the 2 of them. For example, if the perpendicular distance here is 9 meters, it means that the couple, the torque here, which is the moment of the couple, will be one of the forces, that's 3 Newton, multiplied by the perpendicular distance between them, which is 9 meters. If you do that, you will have 27 Newton meters, and that is the torque or the moment of the couple. So with that, I hope we have come to the end of this topic. We have been able to define different concepts under this topic. We have been able to talk about the moment, torque, couple. We have also been able to use several methods that are available for us to solve equilibrium problems requiring 2 vectors, 3 vectors, and so on. Until the next time, thank you once again.